All right, I changed my title a bit and my topic. It used to be Impact of Baryonic Physics on Dark Matter Detection Experiments. Instead, it's now a question, an off-center density peak in the Milky Way's dark matter halo. And as you know, oftentimes when the question is, when there's a question in the title of a talk, the answer is no. In this case, I'm going to argue that the answer might be yes or maybe. This is work that's coming out hopefully very soon, maybe next week. It's a paper that's pretty much done, and my collaborators on this are Javier Agüedes, Annalisa Pilipic, Piero Madao, and Lucio Meyer. So the motivation here is the recently reported 130 GeV gamma ray line in Fermi Gamma Ray Space Telescope data from the Galactic Center. This might not sound like anything that you care about, but I think you should care about it because this might actually be the long sought after detection of a non-gravitational signature of dark matter. It could be from dark matter annihilation, so that should be of interest to you. Just a brief review of what has been reported. Christoph Weniger was looking in the central regions of Fermi, so this is central regions of the galaxy in Fermi data, and he defined kind of an optimized region of interest within which to search for such a high energy line signal. And in this case, he searched for a bunch of different regions of interest. In this case, I'm showing the one that was motivated by an inosto profile. And he indeed found an excess of gamma rays, photons, at about 130 GeV compared to sort of the background that you see at lower energies. Motivated by this, Su and Finkbeiner looked at this. They took a little different approach. They fit templates to the gamma ray data that were determined from lower energy, and then produced a residual map. So the templates included a galactic spectrum, or a galactic template, and a galactic diffuse region, and a few other templates. They subtracted those off, ended up with a residual mass that had a very clear excess in the center. So then they started looking in more detail at the spectral distribution of the photons that are contributing this. And they also pulled out a very clear sort of spectral feature, a very narrow feature around 130 GeV. Right, this has very high statistical significance, greater than 5 sigma, in fact, even when you account for the sort of look elsewhere effect. So, right. So the question is this dark matter annihilation? So the first thing I wanted to point out about this is dark matter annihilation is not some kind of obscure or ad hoc process. It's really built into the theory of, or particle theory of dark matter. The relic abundance is supposed to be set by a freeze out of dark matter annihilations in the early universe, and so even today you might expect to see dark matter annihilation in sufficiently dense regions. Now typically the annihilation proceeds here, like schematized here on the right, through some exchange of some force particle, and you produce standard model particles. So for example, gauge bosons, W's or Z bosons, or quarks, and then those would decay, hadronize, and produce pions, and that would those would decay and give you a very broad gamma ray spectrum. So that's not what we're talking about in the previous observations. Those were instead very narrow monochromatic features. And you can also get that from dark matter annihilation, but you have to go to the next level in the expansion. You have to go to a loop level diagram, so there's an additional exchange particle. And here's a bunch of examples in sort of standard particle physics models of what dark matter is. These all end up producing monochromatic gamma ray photons. But there's a price to be paid for that, which is that now you have additional vertices in your Feynman diagram, so you get additional powers of the coupling, and so your expected event rate or branching ratio for these line photons is suppressed by a factor of 100 or even 1,000 or 10,000. So naively you would not expect to see a line photon in as the first signal of dark matter annihilation from gamma rays. But you know, that shouldn't rule out the dark matter interpretation, because there certainly are models in which you greatly enhance the line annihilation compared to the continuum gamma ray production. And those would not be then standard vanilla dark matter models. They wouldn't be straight up neutralinos, but there certainly are models, singlet dark matter proposed by Stefano Propumo, or a model called Higgs in space, tentatively, tantalizingly, I mean, is an example of models that can give you lines over continuum photons. Now, this doesn't mean that this necessarily is one. There's certainly other worries that you have to address. Here's one brief example. If you select a subset of photons that are arriving from below the horizon, those photons are typically produced by cosmic rays scattering in the atmosphere of the Earth, and they produce some gamma rays. So if you only look at those photons, they should have nothing to do with dark matter annihilation. They're just produced in the atmosphere of the Earth. And then if you further restrict yourself to a very narrow range of those photons, namely those that are hitting the lat detector at an angle between 30 and 45 degrees. Well, if you look at that subset of photons, you do in fact see a similar feature at the same place. So this is somewhat worrisome. Maybe this just means that this whole effect is just due to some systematic. If you talk to Su and Finkbeiner, they argue that even if they get rid of all photons that have this incidence angle in the detector, they still see a significant signal. So, but this is something that one should worry about. There's also some astrophysical explanations. It's not very easy to do. We don't really have many mechanisms that can give you a very high energy narrow line feature, but there are some out in the literature. I'll mention briefly here. If you have a pulsar that for some reason produces monochromatic electrons at 130 GeV and you're surrounded by a fairly low energy photon bath, then you can get inverse Compton scattering in the Klein-Nishina regime, and that would potentially give you a very narrow gamma ray line feature. And there's some trouble with this explanation because it would seem to require multiple pulsars that all are producing monochromatic electrons at 130 GeV, so that doesn't seem terribly likely either. Okay, so that's my sort of background here on the story about the 130 GeV line. One more thing about this, it doesn't seem to be completely centered on the galactic, on Sagittarius A star in the galactic center. Here's if you collapse the signal in latitude, so it's plotted versus galactic longitude, you can see that it actually peaks a little bit off-center, about 1.5 degrees from galactic center in the disk plane. So you might think that, doesn't this make it completely implausible that it could be dark matter annihilation? Shouldn't the dark matter be centered at the galactic center, and therefore the signal should also be centered at L equals 0, B equals 0? And in the rest of the talk, I want to argue that maybe that is not the case. Maybe this is actually not a strike against dark matter annihilation. So offsets, can you find in nature offsets between the maximum of the dark matter density and the minimum of the potential, the dynamical center of systems? And in fact, you do often see this, especially if you look in galaxy clusters. Quite commonly, you find that the centroid of the X-rays is displaced from the center of the strong lensing map. That's what's shown here for a sample of 38 clusters. Even if you select only clusters that are relaxed, that's the dashed line, even those show offsets of multiple tens of kiloparsecs between the center of the X-rays and the center of the potential. If you look at here for a sample of 10,000 slowing galaxies, this came out last week, there's a distribution of offsets between the strong lensing center and the position of the BCG. And so it's a log normal, and it's centered at a few tens of kiloparsecs. Going to scale, I mean, we're talking about galaxies, so maybe we should ask not about clusters, but about galaxies, and there's also some examples there. Here, if you look at an analysis of the thing samples, so they have it's a bit hard to see here from these plots. Look at this inset. The cross is the dynamical center as determined from two-dimensional rotation curves with H1, and then it's centered on the photometric center determined from infrared. And so in most of the things galaxies for which there is a well-constrained photometric center, there is no offset, 13 out of 15. But for two of these galaxies, there is a little bit of an offset, about greater than 2 radio beams, or between 1 and 2 radio beams. So that corresponds to about a few hundred parsecs. So such examples exist. So I'm looking at this in a simulation, the Eris simulation. At the moment you can't see anything, but okay, there it goes. This is a cosmological SPH galaxy formation simulation. I think we're going to hear a lot more about this tomorrow. There will be several talks on Eris. At this point, I just want to say that this is a high resolution, one of the highest resolution simulations that produces a realistic looking Milky Way galaxy disk. It has 7 million dark matter particles, 3 million gas particles, 9 million star particles, and it includes a whole bunch of physics prescriptions, including a blast wave supernova feedback prescription from Stinson et al. That allows it to produce a very realistic extended disk with a low bulge to disk ratio, for example. And it matches the many observational constraints of the Milky Way, as explained in more detail in Javier Arguedes' paper from last year. So I'm using this simulation to look at offsets. Maybe this is a good point to point out here that if you look at the very center, there is kind of a stellar bar that is spinning around here in the center, and I think that has something to do with this offset. Oh, I should also mention we have a dark matter only counterpart, Eris dark. It doesn't have any baryons, but it has the exact same initial conditions. So this is nice because we can do direct comparison and look at the effects of baryonic physics here. All right, so looking at the central regions, what I'm showing here are slices of the dark matter density field, and they're centered on the dynamical center, which is here identified with a minimum of the potential. So this on the top panel is for Eris. This is a slice through the center, through the disk plane, and these are two perpendicular slices to that. And the point of maximum dark matter density is marked with the red cross here, and again, the center, the dynamical center is the white cross. So as you can see, there is kind of an offset here. In this particular output, it ends up being about 260 parsecs, which is only a bit more than 2 softening lengths. So we are gravitational softening lengths. So we are talking about the very, very center of the simulation. It's very clearly at the resolution limit. And so I think if I'd only seen this plot, I wouldn't really have believed it at all. But then when I also made the similar plot for purely cold dark matter only simulations with the exact same resolution, so Eris dark, there you don't see any such offset. And in much higher resolution cold dark matter only simulations via Lactea 2 and G-Halo, there's also no such offset. The maximum of the dark matter density coincides with the minimum of the potential. In order to make these kind of plots, I do have to smooth the density field with some kind of Gaussian kernel. These images are shown for smoothing equal to 1 gravitational softening length. This plot shows you how it changes if I vary the smoothing. Of course, if I smooth with an arbitrarily wide Gaussian kernel, the offset goes away. And if I have a way too small smoothing, then you get shot noise, and then you can get arbitrarily large offsets. But I think between 1 and 2, smoothing with between 1 and 2 gravitational softening lengths, you very clearly see that in the simulation with baryonic physics, there's a significant offset, and the offset remains below 1 softening for Eris dark, the dark matter only counterpart. Now this is just one output time. Thank you. If you look at as a function of time, there's quite a lot. This is not just a fluke. It does actually persist in time. So here's measured the same output, the same offset as a function of time for all the outputs in the Eris simulation, and you can see that for Eris dark, it remains below 1 softening length for the entire duration of the simulation, whereas in Eris dark, it seems to start rising above 1 gravitational softening of about redshift 1.5, and then averages out or remains at about 340 parsecs, so about 3 gravitational softening lengths for the duration of the simulation. This does seem to coincide with a kind of a formation of a flattening of the central density profile in Eris. So that's what's shown here. If I just plot an average enclosed density profile at redshift 0, there's clearly sort of a flattening. In fact, in this way of plotting it as a mean enclosed density profile, it becomes completely flat versus in Eris dark, where it still remains somewhat cuspy towards the center. Here's measuring the slope of the density profile at the nominal convergence radius, which is out by roughly 1 kiloparsec, indicated here with these squares. And you can see for Eris dark, it's consistent with NFW, but then in Eris, there's clearly a flattening of the density profile. And so the time at which this flattening occurs is about the same time at which this dark matter offset starts to kick in. So maybe this is indicating that there's a kind of a common mechanism. The typical Eris outputs are spaced 35 megayears apart, which is really too long to do any kind of analysis of this, dynamical analysis of this offset. So we Javier reran the last 100 megayears of the simulation with a much higher cadence outputs, so producing an output every 1.5 megayears. And here's sort of visualization of the central 2 by 2 kiloparsec region. And you can see that well, first of all, the first thing to notice is that the offset typically remains close to the disk plane, which is indicated here with this gray square. The typical distance of the offset is, as I said, 340 parsecs, but the typical vertical displacement is only 60 parsecs, so it's usually close to the disk plane. It doesn't appear to be stationary, and it also doesn't appear to be very coherent. Sometimes there's even 2 kind of peaks, so this is what it looks like. Now, possible explanation for the rest of our talk. I'm just going to go through a few possible explanations. The first one that you have to check is this just a Poisson fluctuation? There's not that many particles in the center, several, like 5,000, 10,000, but maybe this is just due to small number statistics. Well, that turns out not to be the case. I just created 500 random realizations with the same mean particle number density as in Eris, and you can see the distribution of both the maximum density and the position at which this maximum density occurred look completely different in this random sample versus in the last 120 outputs in Eris. So clearly it's not just a Poisson fluctuation. Could it be some kind of a subhalo that has not completely been disrupted? Maybe because there's kind of a core in the center, so then dynamical friction would be inefficient, and so maybe it could survive for a much longer time than you would normally think. Well, it would have to survive for many, many hundreds of dynamical times, so that's a little bit worrisome. But also, if you actually look at all the particles that are inside one gravitational softening length of the maximum dark matter density at one time, and then just look 1.5 megayears later, those particles have completely dispersed through that central volume, and they're no longer close to the new maximum density. So it's clearly not some kind of bound coherent structure, and instead it might be more of a density wave-like excitation. So could it, or before I get to that, maybe I should briefly discuss, maybe it's an external perturbation. Maybe a satellite is flying by and is kicking the stars and gas, which could be self-bound. They don't need the underlying dark matter halo to remain bound. So if you just kick that self-bound stellar distribution, it could maybe be sloshing around inside the dark matter halo. That could give you such an offset. And it turns out actually, it's a bit hard to see unfortunately, but at around redshift 1.3, there is in fact a subhalo that flies by Eris, and that would be a candidate for such a perturber. So when I saw this, I thought maybe this is the answer. But then when I looked at the position of the potential minimum in absolute coordinates, that's what's shown here in this box in color, and redshift 1.3 is this point here, and there's no particular kick or any kind of displacement of the potential minimum that could correspond to this. So I don't think this is the answer either. So instead, the last thing that I explored is a resonant interaction with the stellar bar. So Eris does have a very pronounced stellar bar at times. It's certainly not a completely axisymmetric stellar distribution. So people have definitely investigated what the interactions between stellar bars and the dark matter halos are. And there can be resonant interactions between the orbits of dark matter particles and the pattern speed of the bar. This has been invoked by Weinberg and Cutts to explain how you could get rid of a cusp and turn it into a core. And actually in a very nice paper by Severino and Khulen, they looked at this in controlled simulations and indeed found particles that were captured in such resonances, and they can give you non-axisymmetric distributions of dark matter. And here particles that are in the co-rotation resonance are kind of in a ring, and they show some kind of localized dark matter enhancement. I looked at this and I decided, well, I can measure the orientation of the bar in the simulation as a function of time, and then I can plot the alignment of the dark matter offset with the bar. I got only 2 more slides, Mark, so I'll be done. And you can see that at very early times, before the dark matter offset is really formed, there's no alignment whatsoever. Then after the dark matter offset appears, it seems to be preferentially close to the orientation of the stellar bar. So that's kind of a hint. Also, if you look at the period distribution, or I've tried to fit a period, tried to find some kind of a frequency in the angular evolution of this dark matter offset. So what I'm showing here is just as a function of the frequency, the chi-squared, quote unquote, of any kind of a periodic signal fit to the offset positions, and you can see that at certain frequencies, at a 70 megayear period, the fit is much better than generally. So there's some evidence for a periodic signal. So this leads me to believe it's not conclusive, but it seems like maybe an interaction with the stellar bar is a promising way to explain this. For dark matter annihilation, this is the projected contrast of the annihilation signal, so of the density squared. And at the moment, at the resolution that the simulation has right now, the contrast is too low to really explain the Su and Finkbeiner result. It's only about 10–15% contrast between the actual galactic center and the maximum dark matter density position. However, we're clearly not resolving the internal structure of whatever's producing this of this density offset. So with higher resolution simulations, it's possible that this contrast would increase and would help with that. So my conclusions, maybe I'll just throw them all up here at once, is that even though at first sight you might think that a 1.5 degree offset of this gamma ray line from the galactic center may be incompatible with the dark matter annihilation interpretation, I would argue that this is maybe not that outlandish actually. Of course, that doesn't mean that it therefore is dark matter annihilation, but I just think you can't use that as an argument to rule out dark matter annihilation. In Eris, we observe such an offset as about 340 parsecs after redshift 1.5, and we don't see any such offsets in pure dark matter simulations. And I've argued that possibly this offset is due to an interaction with the stellar bar. More generally, my conclusion is do not ever extrapolate density profiles obtained from pure dark matter simulations all the way to the galactic center in order to get ideas about what things like dark matter annihilation should be giving you. Thank you.